Hello and welcome back to 3D Additive Fabrication. My name is Zander, and today we're going to cover the introduction to fused deposition modeling. But before we get started, this is actually going to be a whole series of videos, so we wanted to give you the opportunity to give us some feedback and some questions, concerns, queries, things you'd like to see an episode about or always wondered and didn't know who to ask. Put it down in the comments, and we will address it, answer your questions, may even make a video about your idea. Without any further ado, let's get into the intro to fused deposition modeling. Over the course of this video, we're going to cover all the key points that you need to know to kick off your FDM machine. Fused deposition modeling, or fused filament fabrication as it was originally known, is one of the most common 3D printing systems available worldwide, with a price tag ranging from $200 to $2 million US depending on the size and capabilities. Due to the widespread availability of FDM machines, it is currently the most common form of 3D printing on the market. Most FDM machines come in small semi-assembled kits that allow you to build your own machine and learn as you go. And in all honesty, this is the best way to get into this technology. It's fairly inexpensive, you learn the pieces as you put it together, and you really begin to see how the technology works for itself. We will also be covering those details throughout the course of this video. And now to look at how does it work. Filament is pulled forward from the spool by the extruder gear. The extruder gear drives the filament through the hot end assembly by advancing the stepper according to how much filament needs to come out. The filament will travel through the heat sink, which will help keep the whole assembly cool, the heat break, which is supposed to separate the heat sink from the heater block and try and minimize the amount of heat transfer, the heater block, which is where all of our heating activity is happening, which houses the heater cartridge and the hot end thermistor, and down through the nozzle into the printed part. As the filament is being extruded, the hot end will travel around on the X and Y axis based on the program provided by the slicer, creating a 2D slice of filament. At the end of each 2D slice, the Z axis moves so the next 2D slice can be printed right on top of the last one, creating a 3D shape. Now that we have a better understanding of how the mechanics of the machine works, you may be wondering, how does the machine know what to do? FDM machines are based on conventional CNC technology and use a form of the G-code programming language to instruct the machine on how to move and advance the filament. Don't know G-code? That's perfectly fine. G-code for 3D printers is written by computer-aided manufacturing software such as Cura, Slicer, Simplify 3D, Materialize, and NetFab. And onto the basics. What you will need to know to get started with an FDM machine. So first and foremost, one of the most important things you're going to need to know is the nozzle diameter. The nozzle diameter is the size of the hole at the very bottom of the nozzle that the filament comes out of. Most machines come with a 0.4 millimeter stock, but you can have a wide variety of nozzle diameters from 0.2 millimeters all the way up to about 5 millimeters these days. And now on to the layer height. This is the distance between each 2D slice. Having a larger layer height value will decrease the print time and reduce the aesthetic quality, creating a stepped appearance to the print. Having a low layer height value will increase the aesthetic quality, creating smoother outer surfaces, but it'll also increase the print time. The layer height is tied directly to the nozzle diameter and should never be less than 25% or more than 75% in most circumstances. For a 0.4 millimeter nozzle, the layer height should never be below 0.12 millimeters and should never be above 0.28 millimeters under regular operation. I can hear the math wizards in the group sighing collectively that those numbers do not represent 25 and 75% precisely. This is due to the fact that most consumer FDM machines have a Z-axis feed screw with a pitch of 0.04 millimeters. This means that you will get the best results on the Z-axis moving in 0.04 millimeter steps. Wall thickness describes the thickness of the outer walls of the print on the XY axis. Typically, you're going to want more than 1 times diameter as a wall thickness, as that can be quite thin. So you will use factors of the nozzle diameter to create your wall thickness. So if you want 3 walls with a 0.4 millimeter nozzle, you're looking at 1.2 millimeters. Top bottom thickness is the wall thickness on the Z-axis. So if you wanted to take the prior example of having a 1.2 millimeter wall thickness, and you were moving in 0.12 millimeter increments, you would need to have 10 layers on the top and bottom thickness. Nozzle temperature. That's the temperature that the filament needs to be heated up to, and it can usually have a range of 30 degrees or so Celsius. It's always best to take a look at what the manufacturer has recommended for that specific filament and then to tune it in from there. Bed temperature is used to help reduce warping at the base and to help keep the print adhered to the table. Most filaments have very specific bed temperatures. Again, check with the manufacturer of the filament and they should be able to give you some good advice on where to start with that. Whew, that was a lot of talking. Infill density and infill pattern, we're not going to go into in high detail in this video just due to time constraints. The key takeaways here are that you want somewhere between 5 and 35%. More is not more in this situation unless you're talking about more time and more material consumed. Speed. Speed relies heavily on the machine you're using and the type of material you're printing with. Typically, suppliers will advise you on basic speeds that you can use, and you can tune in your machine from there as you get to know it. Cooling refers to the filament cooling fan. This is useful with some materials like PLA, but conversely, it can lead to some problems and potential print failures when being used with more complex materials like ABS and polycarbonate. When you have overhangs or long bridges, you're going to want to use structuring. This creates small towers or a line of filament that's easy to break off, that will be enough to hold the material above it that wouldn't have anything to print on top of if it were not for the structuring. And now we're going to take a brief look at build plate adhesion. This is the most important topic in fused deposition modeling, and we're going to do a more extensive video about it in the future. But the key things that you need to understand right off the bat here are the different types of build plate adhesion systems used within the CAM software. A skirt is 2 to 5 lines printed around the outside of the part that don't directly connect to the part. This is typically done more for purging out the nozzle of old material before starting a print, although I have heard it argued that the heat that it focuses around inside the ring can help adhere the part to the table. A brim is very similar to a skirt in a lot of ways, except for the fact that it'll actually attach to the part and will typically be 5 to 16 lines. This can help prevent warping, especially in materials such as ABS and PETG. And then finally, we have a raft. A raft is actually a structure of 5 to 10 layers printed underneath the part that the part is adhered to that prevents warpage and pulling off the plate. This is very commonly used with materials such as ABS and polycarbonate. By default, most machines have an aluminum plate that's heated through an element underneath the table. First we have glass, which will help improve the surface finish, but can be harder to adhere to and usually requires hairspray or glue stick to help bond. Second, we have painter's tape, which was used with materials like polycarbonate, ABS, and other materials like that to increase the binding to the table. But generally, I find that a build tack or a flex plate is the best way to go for most general materials. As far as adhesive and relief agents go, hairspray is by and far the most common that you'll see. You want a high hold, get the highest number on that hairspray you can, and don't be afraid to ask for help. Beyond that, white glue sticks are also very good for adhering to the table. For more exotic materials such as ABS or ASA, slurry is used, which is a mix of the chemicals and the material that are melted down onto the table. Beyond that, there are professional adhesives made by 3D printing companies that you can also look to if you're really having problems getting that print to stick. With FDM, there's a wide variety of both plastic and metal materials that can be used to print. Most commonly for beginners, you're going to use a lot of PLA, ABS, PETG. These are kind of the mainstays of the home 3D printer. But beyond that, there are more complicated materials that can create amazing 3D prints like PEEK, PC, nylon, carbon fiber filled, and polypropylene for flexible parts. Beyond all those fine plastics, you can also print in copper, aluminum, and tool steels on specific machines. It's important to keep in mind that these materials will require post-sintering and they will not be 100% dense as some of the binding agent is lost during the sintering process. And for our final long-winded slide, the applications of FDM-FFF printing. Typically, FDM-FFF is used for prototyping new products and product development, concept parts, short-run production parts, and my favorite, fixtures and gauges. Now to see how it actually works. Watch the head as it moves around, keep in mind that it's laying down plastic on every pass, moving the Z up, and then laying down another 2D slice of plastic. Now, obviously this video has been quite a bit time-elapsed. This was a 2.5-hour program, and we're giving it all to you right here. I need a solid gold violin. Oh, hello there. Welcome to the end of the video. Make sure you like, subscribe, leave a comment if you got any ideas, and we'll see you again.